You know, when we talk about AI, we always hear about the big breakthroughs, right? But what we don't often see is the stuff happening behind the scenes, the actual tools that researchers are using every single day to make those ideas happen. And it turns out, one specific tool has pretty much become the secret language of almost every modern AI research lab.
So that's the big question for us today. Why PyTorch? I mean, what is it about this framework that's made it the absolute go-to for so many people who are really on the cutting edge? And the answer? Well, it's not just a list of features. It's actually about a whole philosophy.
Okay, so to really get into it, here's how we're going to break it down. We'll start with that core philosophy, then get into its technical architecture. We'll see how it automates research, explore its huge ecosystem, check out some mind-blowing science, and then finish up with a look at its future, which, spoiler alert, is all about speed.
All right, first things first, this whole research-first philosophy. And look, this isn't just some slick marketing slogan. PyTorch was built from the ground up to feel right for actual research, which, as you know, can be messy and involves a ton of trial and error. The whole point was to get the tool out of the way so scientists could just focus on, well, the science, instead of wrestling with their software.
And the absolute heart of this idea is something called define by run. It sounds super simple, but it is a massive deal. It just means when you write a line of PyTorch code, it runs, right then and there. Now, that might sound obvious, but for anyone who used older frameworks, that's a world of difference. It means you can just use your normal Python debugger, you can print stuff out, you can poke and prod your code just like any other script. It just feels, well, Pythonic. It feels natural.
And this table just lays it all out perfectly. On one side, you've got the old way, static graphs. Think of it like creating a detailed architectural blueprint before you even start building. It's rigid, and if something goes wrong, good luck figuring it out. It's a headache. But on the other side, you have PyTorch's dynamic way. Here, the blueprint gets built as you go, step by step. This means you can just throw in normal Python stuff, like an if statement or a for loop, right into your model. And debugging? It's just a normal Python error. For a researcher, that kind of flexibility isn't just nice, it's a total game changer.
Okay, so we've got the philosophy down. Now let's get a little more technical and see how that philosophy is actually built into the code. It all comes down to three core pieces that everyone using PyTorch deals with: tensors, gradients, and what are called neural network modules.
So, let's break it down. First, you have the torch.Tensor. That's your basic building block for data. It's basically a superpowered array that you can stick on a GPU to make things go fast. Then, there's torch.autograd. This thing is awesome. It's like a tape recorder that's always listening. It records every single calculation you do so it can automatically figure out the gradients for you. And all a gradient really is the secret recipe for how to tweak your model to make it a little bit better. And finally, torch.nn is your toolbox. It's full of pre-built Lego blocks, like different layers, that you can snap together to build your models.
And here's how all those pieces dance together. Seriously, training pretty much any model in PyTorch follows this exact same 5-step rhythm. You do a forward pass to get a guess, you calculate how wrong that guess was, that's your loss, you zero out the old gradients, then you do the backward pass. That's the famous backpropagation step, where AutoGrad does its magic and calculates all the new gradients. And finally, you use an optimizer to nudge your model's weights in the right direction. This loop, this simple 5-step process, that's basically the heartbeat of all of deep learning.
But let's be real, research isn't about training just one model. It's about training dozens, maybe hundreds of them, right? And this is where PyTorch really starts to pull away from the pack. It's not just the core library, it's the ecosystem of tools built around it that lets you go from messy, single-use scripts to clean, reproducible science.
And one of the biggest tools for that is PyTorch Lightning. Its whole mission is simple, but it is so powerful. It's all about decoupling the science from the engineering.
What that means is you, the scientist, get to focus on the fun stuff, the stuff on the left. You know, your unique model architecture, your clever loss function. Lightning handles all the dirty work on the right, all that repetitive training loop code, the nightmare of setting up multi-GPU or TPU training, stuff like mixed precision, all that boilerplate. It means you can take your code from a laptop to a massive supercomputer pretty much without changing a thing.
And then, to keep track of all those experiments, there's this amazing tool called Hydra. Instead of hard-coding your parameters, you define everything, learning rates, model sizes, you name it, in simple config files. You can tweak things on the fly from the command line. But the absolute killer feature is multi-run, With one command, you can launch a whole grid of experiments, automatically trying out every combination of parameters you want. It's just so good for doing systematic research.
So you've got this great, structured way of working, and then that whole thing gets supercharged by this massive, thriving ecosystem. Because PyTorch isn't just one library. It's the bedrock for an entire universe of specialized toolkits that make it so much easier to get started in all kinds of different scientific fields.
I mean, look at this list. You've got Torch Vision, which is the go-to for computer vision. PyTorch Geometric is the king of deep learning on graphs, which is huge for things like drug discovery. There's Torch Audio for audio, Torch RL for reinforcement learning, and of course, you can't forget the Hugging Face Transformers library. It's basically the undisputed standard for pretty much all modern NLP work. It's just a massive advantage.
Okay, so this is where it gets really cool. What happens when you give all these powerful, super flexible tools to scientists? Well, they start doing things with them that nobody ever expected. Things that go way beyond just deep learning. PyTorch is basically turning into a general-purpose, differentiable programming language. And that lets researchers mix and match machine learning with classic, first-principle science.
Check out PhoTorch. This is wild. The researchers here didn't even build a neural network. Instead, they took the classic textbook equations for photosynthesis and just wrote them out using PyTorch code. Then they just let PyTorch's optimizers and AutoGrad engine do the heavy lifting to fit the equations parameters to real-world data. And the result? It was 4 times faster than the specialized software that already existed.
Well, how about CTorch? This is for making CT scans better. What the team did was they took the actual physics of how an X-ray projector works and turned it into a custom layer inside a neural network. Think about that. It means the model isn't just learning from data, it's also constrained by the laws of physics. That's what people mean when they talk about physics-informed machine learning, and it's incredibly powerful.
And this is really the new frontier. With TorchSim, they built an entire physics simulation of atoms inside PyTorch. And because the whole thing is built in PyTorch, it's all differentiable, which means you can do something that sounds like it's straight out of science fiction. You can backpropagate through time. You can run the error signal backwards through the whole simulation to fine-tune the fundamental physics. This is a whole new way of doing science. It's trainable, differentiable physics.
Now, for a long time, there's this one little catch. For all its amazing flexibility, PyTorch's dynamic style was sometimes a bit slower than those rigid, static frameworks. It was a classic trade-off, flexibility versus raw speed. But with PyTorch 2.0, that trade-off is basically gone. The whole future is about getting that amazing flexibility and best-in-class performance.
And how do they do it? You're looking at it. 1 single line of code. You just take your model, wrap it in torch.compile, and that's it. Under the hood, a whole new compiler backend kicks in and does all this amazing optimization. And you don't have to change anything else about your code. It's just magic.
And the impact of that one line? It's huge. We're talking typical speedups of 1.5 to 2 times, sometimes even more. This is basically democratizing high-performance computing. You don't have to be some wizard who writes low-level GPU code anymore to get these kinds of speed boasts. You just add that one line.
And this quote just nails it. This is about getting the best of both worlds, no compromises. You get the screaming fast performance you'd expect from a static, compiled framework, but you get to keep the fun, flexible, defined-by-run way of working that made everyone love PyTorch to begin with.
And that really brings us to the big takeaway here. We've seen PyTorch grow from just a tool for AI into this whole new language for doing science. It's letting us treat the laws of physics themselves like a trainable model. And that leaves us with a really exciting question for the future, doesn't it? When your tools are this powerful, when you can literally differentiate through a physics simulation, what new discoveries are we about to unlock?